Okay, here we go. It's time for a marathon. Am I crazy for doing this? Probably. But in any event, this is an Honors Algebra 2 exam review, as indicated here. Not really important where exactly it's from, but it is a very comprehensive and formidable Algebra 2 review packet. So there are plenty of problems here. Definitely pause the video at some moments to try them first before I walk through them. But without any further ado, I'm not going to really provide too much depth and explanation. I'm just going to I'm not going to explain a lot of deep theory and definitional stuff, but I will present my methods, and I will be commentating along as I go through this. No clue how long this is going to take, but it's likely going to take several hours. Okay, let's start with the easy stuff, bread and butter, factoring. One of the most important skills when it comes to doing like a high school level math or elementary level math up to calculus is factoring. And factoring is going to continue even through number theory and other fields of higher level math. So in order to factor this, we're going to take out, I zoomed this picture in a lot so that you can really see what's going on, but also so that I can have space to write, because my pen can only get so small. So here we have 1 minus 81x squared. This is, of course, a difference of squares. This is a squared, this is b squared, which is going to turn into a minus b. B is 9x, a plus b. And this is fully factored. Starting off pretty nicely. We move on to number 2. Factoring. This is a sum of cubes. This is a cubed, this is b cubed. So the formula for that is a plus b times a squared, which is x squared squared, minus ab, which will be x squared y squared. You could also put them both together and square it, plus b squared. And this will be an irreducible quadratic, meaning you won't be able to factor this down anymore. Okay, number 3. Factoring this, we're going to employ the grouping method of factoring, where we have 4 terms, and that always kind of smells like grouping. We're going to group these together 2 at a time, and we're going to factor something out of each group. So here x comes out of the first group, leaving us with y plus 5. And then we should be able to factor something out of the second group such that it leaves the same y plus 5 factor. That would be negative 2. And now we can factor out the common group factor of y plus 5. That looks quite hideous, doesn't it? So we'll have x minus 2. They each have the partner of y plus 5. There we go. Fully factored. So we're starting off very light. Trust me, it will get a little more intense. Like here. Here we have something that's fairly intense, right? So let's take a look at this. We have this sort of quadratic looking thing, and if I had just given you this, you could maybe factor this quadratic. And then if I gave you maybe just this, excluding the minus sign, that would also be some kind of interesting quadratic. So I see some perfect squares here. Those 2 are perfect squares. Well, so is really 25x squared is perfect square, so it's plus 9. And then 4a squared is perfect square, and so is b squared, obviously. So a good guess is to say maybe this is 5x and this is 3. The minus in between indicates that this is a minus, so this would be 5x minus 3 squared minus, let's try that again, this is 2a and this is a b. But if you notice, if I factor the negative out, then this is going to have 4a squared with a minus 4ab and a plus b squared. So let's think about it like that. 2a and b with the minus indicated in the middle. So this would be 2a minus b squared. And then we use the difference of squares factoring. This is your a squared, this is your b squared. So we'll end up with a minus b, which is minus 2a and plus b, and also a plus b. So 5x minus 3 plus 2a minus b. This is fully factored. No more squares. Very interesting. Okay, pretty light still, pretty light. Factorize this. Now this is clearly not a perfect square trinomial because 21 is not a perfect square. That's not your b squared. So we might have to use these sort of old school methods. Split the middle, right? Where we multiply and split the middle. So we're going to take 4 times negative 21, which is negative 84. And here we have negative 25. So we're looking for two numbers which multiply to negative 84, and they add together to make negative 25. And it's really tempting to think, oh, well, I know 21 and 4 multiplies to 84, and if I add them together, I get 25. However, you have to be careful because the top value is negative, meaning that one of these needs to be negative and one of these needs to be positive. And if I take 21 and 4 with one negative, one positive, it will not combine to 25. So that being said, we need bigger number than 25 to be negative and a smaller, small number to be positive. This is going to be 28 and 3. And the way that this works is we split the middle term into these two pieces that we just discovered, 28x and plus 3x, because they after all combine to make negative 25x. And now we have our grouping situation on our hands. We're going to group factor these. Here's 4x. There are other ways to do this, but this is just the way that I'm choosing to show you. Plus 3 times x minus 7. And therefore we can factor out the group factor of x minus 7, leaving us with 4x plus 3 times x minus 7. Like that. Cool. First page is complete. All right. Here we have an interesting quadratic situation, but the expression here is a little bit different than what we might expect. We're going to make a substitution. Let's just call this like, I don't know, a. And therefore we have something like 4a squared plus 19a minus 5. We can do this sort of diamond factoring here where we multiply the top. Makes negative 20. And we have a plus 19 here. We need two numbers which multiply to this. We need the positive number to be bigger and the minus to be smaller. So this is going to be 20 times negative 1. And therefore we can split the middle as follows. 4a squared plus 20a minus a minus 5. And now it's time to employ group factoring. Keep in mind, everybody, that a was a replacement from the beginning. So we're going to have to replace things back. Let's take out 4a, leaving us with a plus 5. And then let's take out negative 1, which will also leave us with a plus 5. And so overall, our factoring is going to be 4a minus 1 times a plus 5. And now it's time to put this substitution equation back. So this would be 4 times x plus 3 minus 1 times, well, just x plus 3 plus 5. And so writing this out proper is going to be 4x plus 11, that's 12 minus 1, and x plus 8. Great. That is fully factored. And interestingly, if you work all of this out, go ahead and do that if you'd like, and then if you work all of this out, you should get the exact same. Okay, moving on to number 7. 2xy squared minus 21xy minus 36x. One thing you should always look for in these factorization problems is a greatest common factor that you can remove to simplify your expression, and then there's less thinking involved later. So we need to look for something in common, and every single term has the x. It may look like everyone has the xy, but this last one does not have the xy. So here we have x to be factored out of everything. We cannot take a 2 out, but you should also be aware that sometimes a number will be factored out as well. 2y squared minus 21y minus 36. And let's go ahead and do our little x factor here. This is going to be two numbers which multiply to make negative 72, and they add together to make negative 21. So we're going to have a larger negative number and a smaller positive number. It's going to be 24 and 3. So we're going to call this 2y squared minus 24y plus 3y minus 36. Okay, so we can employ group factoring once again. When you have four terms like this, it sort of smells like group factoring. So we have 2y, and that's going to leave us with y minus 12. If we factor a 3 out, this is also going to leave us minus 12. So altogether, don't forget that there was an x in front, just kind of hanging out, waiting for everybody to group together. We have x times 2y plus 3 times y minus 12, and that is fully factored. Okay, making some pretty good time here, but the problems will absolutely get more complicated and tougher. Let's use the greatest common factor method here again. Now I'm looking for what's in common of all of the terms. We have x, y in every single term, and we cannot quite take out a factor of 3, unfortunately. So we're going to have to pull out a negative x. I guess we don't have to take the negative x out, but I'm going to choose to take out negative x, y, and that will leave us with positive 9x squared. That's kind of why I wanted to take the negative out. Minus 10x, be careful, plus 25. There we are. So here we are. Yeah, let's take a look at that. Did I factor everything correctly? Yes. Took the negative x out, took the y out. Okay. Took an x out, took a y out. Oh, this should still be a 30. I'm sorry. I knew something looked off. This should still be a 30. That's looking better. Okay, so now it does seem like these might be some perfect square trinomial here, because this is a perfect square and this is a perfect square. So let's go ahead and try it. In fact, I think we saw this one earlier, did we not? Yeah, I think we saw basically this one, just the reverse. So instead of 5x minus 3, probably going to be 3x minus 5. 3x minus 5 squared. You can confirm that that is going to give us negative 9x squared minus 30x plus 25. And this will be our complete factoring. There we go. Number 9, aha, some more tricky business. So number 9 is a little bit tricky. Of course, we see that there's a common factor here of x and x, and it's possible that maybe a number comes out as well. Well, 145, this is simply 5 times 29. It's prime, those don't break down anymore, and this is just simply 2 times 3 for the 6. So no common factors as far as numbers go. The real tricky thing here, though, is that we're going to have to take out the smallest exponent. And when we do that, you have to realize that the smallest exponent is negative 3/2. You also have to realize that when we factor out this smallest exponent term, so we're going to take out x, and we're also going to take out 4 plus x squared to the negative 3/2, we're basically dividing this factor out. And when you divide, we subtract exponents. And so that's going to leave us with 145x, not x squared anymore. We took an x away from there. And then times 1, because we removed the entirety of this 4 plus x squared minus 3/2. Plus 6 times, what's going to happen here now? If we're subtracting if we're subtracting negative 3/2 from the exponent, this is now going to be an exponent of negative 1/2 minus negative 3/2 is just negative 1/2 plus 3/2, which is just 2 over 2 or 1. And so this will be left with x squared, or 4 plus x squared to the 1 power, sort of. And so all there really is left to do is to kind of simplify some of these things. We can multiply this and rearrange the terms inside to get 6x squared plus 145x plus 24. And interestingly enough, this will factor down a little bit more. So we still have a little bit of work to do here. If we make our x multiply 6 and 24 to get 144 and positive 145. So we're looking for two numbers that multiply to make 144 and add up to 145. Of course, this is 144 and 1. So we're going to go ahead and split the middle term. Plus 1x plus 24, and we can employ group factoring now. So here's the group factoring. 6x, this will be x plus 24. And then if we take out a 1, this will also be x plus 24. So altogether, people, we have x times 4 plus x squared to the negative 3 halves times, oops, that doesn't look like a half. That also doesn't look like a 2. There we go. I swear I can draw 2s. Then we have 6x plus 1 and x plus 24. And this will be fully factored. Yes. Quite intense what we're going for here now. Okay, let's continue in the same vein of greatest common factor usage. Here, what we're going to do is we're going to divide out the common factor. Now, this is to the 5 halves. This is to the 3 halves, and this, even though it doesn't look like it, remember that a square root is the same as a 1/2 power. So therefore, we have a common factor of x squared plus 2 to the 1/2 power. And if you want, you can go ahead and put that in a square root, but what's really important is what's going to be left. So when we divide out numbers with the same base, we subtract their exponents. So we're going to be left here with x squared plus 2 to the 4 over 2, which is just squared, and x squared plus 2 to the 2 over 2, which is just to the 1 power. And now this is not too bad. We're going to end up with something like, let's call this a. Let's call this a. We're going to end up with something like a squared plus 2ax plus x squared. And this is a perfect square trinomial. You'll notice that this is a perfect square. This is a perfect square. So we'll end up with a plus x all squared. But a was a substitution for x squared plus 2. So really we're going to have square root of x squared plus 2, parentheses, x squared plus 2 plus x squared, which I guess can turn into something, right? X squared plus x plus 2. I guess that cannot simplify. We can't factor that down more is what I mean. If one of these were, if this was a minus, then we could actually factor it down more, but otherwise we're going to leave it like this. Okay. So some tricky substitution is also valid in these cases where it's looking like a quadratic, but there's a little more flavor to it. All right, let's take a look at this. Factoring x squared y squared plus 9a to the 4th. Well, this gets a little bit tricky because here we do have perfect squares. This is just xy perfectly squared plus 3a squared perfectly squared. But there's not really a sum of squares factorization that we can do without using this term I. So if we want to use a sum of squares, this is kind of a special case. We could have a and b, but rather than a minus b, a plus b, it would be something like this. It would be a plus bi times a minus bi. And so that factorization would lead us to say xy plus 3a squared I, that's an I, times xy minus 3a squared I. And that would probably be the best that we can do. Yeah. All right, time to simplify. We're simplifying cube roots, radical expressions. The best way to do that is to try to simplify this by pulling out perfect cubes. 24 is equal to 8 times 3. So if we have that in a cube root, the cube root of 8 is very nice, and it sort of pops out of the root as just a 2, leaving us with cube root of 3. So now these are compatible. We have 2 cube root of 3 minus 2 cube root of 3. Those will just cancel. And let's see what happens here. If we take out, again, a perfect cube factor of 125 in this case, that will pop out nicely as the cube root of 125 times the cube root of 3. Cube root of 125 is just 5. So the overall result here, and don't forget that it's multiplied by 2. So 2 times this will just give us 10 times the cube root of 3. And it's all simplified very nicely. Okay, now we're going to continue working with some of these. You'll notice that these can get broken down quite a bit, so let's see if they all get broken down to the same radical. Well, if I take out all of the perfect squares here, notice these are square roots, not cube roots anymore. Root 4 times root 3, which is just 2 root 3. If I break this down, I get root 9 times root 2, which is 3 root 2. That one is a different type of radical. If I break this one down in terms of perfect squares, the biggest one I have is 36 times root 3, so that's going to be 6 root 3. And then if I break this down the most I possibly can, this is going to be root 36 and root 2, so we'll have 6 root 2. And now we can just combine like terms. So these root 3's are going to connect. 3 times 2 is 6 plus 6. And then if we combine these together, we have negative 30 and negative 6, so negative 36 root 2. Is this a positive or is this a negative? You decide. Rewrite this expression in 2 ways. Okay, so now they're going to have us get a little fancy with the exponent work. Just using rational exponents, pretty straightforward. If you're expressing this as a base with some kind of fraction exponent, that's what rational just means. It's just a fancy word for fraction. So this will be a to the 5/9 times b to the 4/6, which I guess we could just call 2/3. There we go. Right, 4 over 6 reduces to 2/3. So that is part A by expressing this in terms of rational exponents. But part B wants us to use a single radical. And so that's going to require the same power on the radical. It's going to require some n that's the same. So how could we possibly express these at the same? Because we have a to the 5/9, which has a denominator of 9, and then we have b to the 2/3, which is denominator 3. So those would not use the same radical, but if we want to use the same radical, we just need the same denominator on the exponent. And so we can change this fraction, kind of like if you were getting a common denominator, really. This would turn into 6/9. And so this would end up with the 9th root of a to the 5th times b to the 6th. Fascinating. Fascinating. Okay, rationalize this denominator. Oh boy, what do we mean here by rationalize the denominator? We basically mean no more square roots in the bottom. How do we eliminate square roots? This is a very important tip to remember in your math career. If you want to get rid of square roots, we can multiply by the conjugate, because that's going to create a difference of squares. So whenever you multiply a term by its conjugate, which in this case would look like this, I call it the evil twin. In this case, it's the good twin. Notice the plus in between, as opposed to the minus in between. That is the difference that makes this the evil twin versus the good twin. And we have to multiply this on the top as well, because technically we're multiplying this fraction by quote-unquote 1. Anything divided by itself, which is non-zero, is 1. And on the bottom, that's going to create some really nice circumstances. On the denominator, we're going to have, this is a minus b times a plus b, which will just leave us a squared, that gets rid of the square root, minus b squared, which also gets rid of the square root. So in the denominator, we just end up with over 4, essentially. In the numerator, it's not so perfect. For some reason, we don't mind having radicals in the numerator. We just want to get them out of the denominator. Why is that? Good question. Not really sure. So we have an a times a. That is still a squared, so that is still going to be x plus 4. And then we have the outer, and then we have the inner. So this is going to be one of these root x times root x plus 4, and two of these root x times root x plus 4. And I guess we can just sort of put it like that. We can multiply radicals by multiplying their insides. And then when we do the last multiplications, that's going to just give us 2x. So putting things together, we're going to have 3x plus 3 square root of x squared plus 4x. And then plus 4. There we go. Wasn't so bad, was it? All right, moving forward, we are about almost 1/6 through this, but not quite. We're about 1/7 through it, realistically. Use one of the special products to compute this. Now, I'm not sure what is intended here with special products, but I can tell you with confidence that if we have some a plus b cubed, this will result in a cubed plus 3a squared b plus 3ab squared. Those are different. The a is squared here and the b is squared here. And then finally plus b cubed. Now if we have a minus as the b, that means that this term will be negative. The squared one will not be negative, but this term will also be negative. So putting this all together, we're going to have 2x squared cubed minus 3 2x squared squared times 3y. I guess I could also be a little more responsible and put plus, but put the negative 3y here where it belongs. Plus 3 times 2x squared times negative 3y, but it's squared now. That's why it will not become positive. And then lastly, negative 3y cubed. So this is just a little bit of work. It's going to leave us with 8x to the 6th power minus 36 x to the 4th times y. You'll notice that as the power of x goes down by 2, the power of y goes up by 1. Then we're going to have plus 54 x squared y squared. See, that happened again. The power went down by 2 on the x, but it went up by 1 on the y. Sort of a pattern here. Yeah, binomial expansion is definitely pattern-based. And then minus 27 y cubed. Bam. Bam, bam, bam. Okay. Let's see what we have here. Now, we need to understand absolute value for a moment. So just understand this. The absolute value of anything is a piecewise function. The absolute value of something is equal to whatever is inside as long as the inside is not negative, whereas the inside is flipped opposite whenever the inside is negative. So it says given that x is greater than 10, what does absolute value of x minus 5 look like? Well, as long as the inside is greater than 0, it will just be x minus 5. It will just be exactly what we're putting in. Because if it were already positive, which means x is greater than or equal to 5, then why would we have to worry about flipping it? But if it is less than 5, then we do have to flip it. Similarly, the absolute value of 10 minus x is going to be exactly what it looks like, 10 minus x, whenever that inside is not negative. In other words, whenever 10 is greater than or equal to x. But it would be flipped to negative 10 plus x, or I guess I can say x minus 10, whenever x is strictly less than 10. Is that right? I think I might have that flipped for some reason. Whenever the inside is positive, that means x is smaller than 10. Ah, yeah, okay, so this is what's flipped. This should be x greater than 10. Got it. So we have x is greater than 10, which means we're going to be using this definition of it. So this expression just turns into x minus 5, because we're satisfying this condition that x is greater than 10, therefore it's greater than 5. And then for the second absolute value expression, we're going to flip it because we're using this condition that x is greater than 10, therefore the inside is negative, right? If x is bigger than 10, then 10 minus x will be negative and we'll have to flip it. So this will be x minus 10, in other words, 2x minus 15. And when x is equal to 10, this is simply a 5. Okay, a little bit of work with absolute value for that one. Scientific notation, what a breath of fresh air. This is really simple. All we have to do is make sure that our number is being adjusted so that we're moving the decimal as many times as necessary to the left or to the right, such that the number is in between 1 and 10. So in this case, we're going to look at 2.1. The thing is, the decimal is to the left of that. How many spaces to the left is it? 1, 2, 3, 4, 5, 6. Very simple. So this is going to be 10 to the negative 6 power. Basically, each power of 10 is a different placeholder, and the minus means we're going to the left. So we've gone to the left 6 places, or we will go to the left 6 places in order to get the true number that we're looking at. So this is part A. Whereas part B, we want to put the decimal right here. We don't want to put it after the 5, otherwise that number is bigger than 10. And we don't want to put it before the 1, otherwise that number is smaller than 1. So if we had it here, just think how many tens, how many placeholders do we have to jump in order to get to the end of this number? Did you count? I counted 11, but let's double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yep, looks like 11. So this would be 1.5 times 10 to the 11th power. Big number. Whoa, mama. Wouldn't you love to make that much in a year? That'd be nice. In fact, to put that into perspective, this is like about half as much money as, like, I don't know, Jeff Bezos or Elon Musk has. It's like half of the dollars. Pretty crazy. Specify the intervals that are described by these inequalities. So we have two inequalities. We're going to have to treat them differently. And the way that we work with absolute value inequalities, because of this flipping behavior that I mentioned, it's either the case, just talking about part A, it's either the case that x minus 5 really is just less than 7, or if it were flipped negative, that would mean that x minus 5 is actually greater than negative 7. So let's solve those two separately. This would mean that x is either less than 12 or x is greater than negative 2. And so the interval for that means x has to be bigger than negative 2, but not including. Otherwise, if it were including, I would put a bracket if there were like a line under here. But it's not including, so it's going to be from negative 2 to 12. Not bad. And here, it's potentially true that x is literally greater than or equal to 5, like if we have x equals 6 or 5 or 7. Or it's possible that x is less than negative 5. For example, if x were negative 6 and you put that in here, it turns it into a positive 6, which is now bigger than 5. See how that works? So it's either that x is a number less than negative 5, or, which means we have to union these two intervals together, or x is bigger than 5, which means from 5 onward to infinity. Okay, very good, very good, very good. Solving for x. Now this looks funky because we have fractions and stuff that are being worked with inside of the absolute value, but let's just simplify the stuff in there first. Let's get a common denominator here, shall we? So if we get a common denominator, we multiply the first fraction by 5 over 5, and we'll multiply the second fraction by 2 over 2. And now this will all be over 2 times 5, or 10. And so this would be 5x minus 5 minus 4x plus 2 over 10. And this is much easier to work with now because this simply is x minus 3 over 10. And we want this again to be greater than or equal to 1. So that means either the stuff inside literally is greater than or equal to 1, or if it got flipped negative, that means that its value was actually less than negative 1. And so we can do a little bit of algebra work just to figure out when is this true. So if x minus 3 is greater than or equal to 10, then x has to be greater than or equal to 13. Whereas on the other hand, if x minus 3 over 10 is less than negative 1, that would mean x minus 3 is less than negative 10. And so x is less than negative 7. And so that's going to carry us from negative 7, negative infinity to negative 7, but not including negative 7. If it were including, we would have a little line underneath here. We do not have that. And we're going to union this with the space from 13 with a bracket, because there is an equals on the inequality. So from 13 to positive infinity, and that's going to be the interval that we take for this. I mean, you could check any of these if you want. You can plug in any number that's between negative infinity to negative 7, or you can plug in any number that's from 13 to infinity, and either way, when you plug that in, you're going to get an inequality that's greater than or equal to 1. Oh, and you take the absolute value as well, because you might get a negative. Okay, so very similar setup in this other absolute value inequality. This time they're looking for something which is less than or equal to 1. So first step here is to simplify everything that is inside of the absolute value. First thing is to get this common denominator. So we're going to multiply the first one by 4 over 4. And we're going to multiply the second one by 5 over 5, all over the denominator of 20. Go ahead and work that out and then simplify. So we'll end up with 4x plus 12, yeah? And negative 5 and plus 25x all over 20. And so combining this, we'll end up with 29x plus 7 over 20. And this needs to be in the absolute value still, less than or equal to 1. So that gives us two scenarios whenever we have absolute value. It's possible that the thing inside of the absolute value is just literally less than or equal to 1. That is possible. Which would mean that 29x plus 7 is less than or equal to 20. This will give us that 29x is less than or equal to 13, meaning that x is less than or equal to 13 over 29. And it's okay that that's not necessarily a nice fraction. That's totally fine. It doesn't matter. On the other hand, it's possible that the thing inside of the absolute value, 29x plus 7 over 20, it's possible this is greater than negative 1. Did I consider that properly in the other one? Yes, I did. I put the negative. It's very important to do that when you're working with absolute value. You need to flip the inequality as well as make it the opposite inequality. Well, that's what it means to flip the inequality. Okay, so 29x plus 7, it's possible that that is greater than negative 20, which would mean 29x is greater than negative 27, which would mean x is greater than negative 27 over 29. And just be careful about where those intervals are. So it's less than this positive number, greater than this negative number, and you can write the interval as follows. Negative 27 over 29, comma 13 over 29. Notice that one of them will have a bracket because this inequality says less than or equals. This inequality says strictly greater. So we're not going to include the negative 27 over 29. We are going to include the 13 over 29. That one is valid. Okay, find all real solutions. This should pretty much scream a quadratic. If it doesn't scream quadratic, then you need to really look at this more closely because there's an x squared in it. Pretty much tells you it's a quadratic. And the way we solve those is we move everything to one side, and we try to factor if possible. So let's go ahead and try to factor that. Looks like it factors nicely. Two numbers which multiply to -12 and add together to -1. That's one negative, one positive. The negative number's a little bit bigger than the positive here, so 4 and 3. That works just fine. And then we're splitting the middle term to create sort of like a grouping situation. And now we can just group factor the first two. Take out a 2x, leaving with 3x minus 2. Can't really take anything out of the first, out of the second one here. You can just take a 1, so go ahead and just take a 1 out. Doesn't really do anything, but it does allow us to group factor this a little bit better. So 2x plus 1, and then we have 3x minus 2. Now, since this wants us to solve, it doesn't just want us to factor it. We need to follow through with the factorization. We need to use the zero product property to say that means 2x plus 1 could possibly equal 0, in which case x is -1/2, or 3x minus 2 is equal to 0, in which case x is equal to 2/3. So we do not get an interval here. We do not get like parentheses with a spread of values. We just get exact numbers. And so that's a lot easier. You can definitely check those if you need to. Plug in -1/2, see what you get. And then plug in 2/3, see what you get. Both left and right side should be equal. Otherwise, that means you did something wrong with your solutions. Same kind of thing here. I suspect this one does not factor. Because they're going to give you a problem where it factors, and then they're going to give you one where it does not factor. So we have to use the handy-dandy, right, quadratic formula. Got to go reference that one. I'm not going to write out the whole quadratic formula in its entirety. I'm just going to plug in the values that are appropriate here. And you'll notice that it says find all real solutions. Why would they specify that? They would specify that because there could be imaginary solutions if, in fact, we get a negative inside of the square root. Fortunately, we don't have that here because we're multiplying by a negative, which is going to turn everything into a positive inside of there. So our x values are -2 plus or minus the square root of 24 all over 2. You should simplify your answers. Don't be lazy. Definitely simplify your answers. So what can we pull out of here? This is the same as root 6 and root 4. Root 4 is just 2. So that works out sort of perfectly, doesn't it? When we divide by 2. We'll have two answers. You can either write it in plus or minus format. I personally don't like to write it in plus or minus format. I like to write them out. So -1 plus square root of 6. And then -1 minus square root of 6. If you want to just write plus or minus, I mean, that's up to your discretion. But I feel like a lot of students forget the fact that there are two separate solutions. And sometimes teachers just want you to put them separately. Like if you have to graph these solutions for some, I guess that's another reason why I'm kind of picky about it. If you need to graph these and put these on a number line, you can't graph two different numbers like at once at the same place. So just separate them. And if you want to use a calculator or something to approximate, that's fine. You should know that the square root of 6 is like a little bit above 2. You don't have to know exactly what it is, but it's like 2.45 or something like that. Okay, now it's time to look at some kind of algebra basics again, but we're going to look at them more closely. So finding the equation of this line in a slope-intercept form that is a specific format. The name kind of tells you what's important in the format. It needs to have the slope, and it needs to have the intercept. That's why we call it slope-intercept. So let's find the slope. They give us 2 points. That's very easy to find the slope if they give you 2 points. Sort of impossibly easy. If you've made it this far, you should absolutely know how to find the slope between 2 points. So y2 minus y1 over x2 minus x1. And it really doesn't matter which one's your 0.1 and 0.2, just as long as you're being consistent. So I could have done -2 minus 4 over 3 minus -1. Doesn't matter, it comes out the same. So we have 2 over -4 or -1/2. That's great. That's the what? The slope. Not done here. Now we need to use the slope along with some point. One of the points, they gave you 2 to choose from. Pick your favorite. If you like 3 or if you like 4, pick your favorite. and we're going to plug that point in. So I'm going to choose this point. So that would be to say -2 equals the slope of -1/2 times 3, and then plus the b. Or if you wanted to say 4 times -1/2 times -1 plus the b. Either way, you're going to get the same answer. Let's see here. Did I plug the -2 in correctly? Yeah, looks good. So like this would just be 4 equals 1/2 plus b. Or this would be -2 equals -3/2 plus b. Now, for some reason, it does seem like that is absolutely a completely different value. Yes, that's because this slope is different. If you're screaming at the screen at this point, totally understand. So 4 minus -2, that's the same thing as just 6. So this will actually be -3/2. There we go. So let's set up our equations properly now. -2 equals -3/2 times 3 plus b, or 4 equals -3/2 times -1 plus b. There we go. That looks better. So in any event, you're going to get that b is equal to 5/2 or 2.5. Again, totally up to you how you want to call it. And therefore, our entire equation, -1/2 x plus 5/2, that is the equation of the line. And you can always check these. Whenever you're given whenever you're finding an equation and they give you points, plug the points back in. Make sure they're actually on the line that you're saying it's on. Because if not, that means you made some kind of like calculation error or something like that. Okay, again, we want slope-intercept form. Slope-intercept form. So we want this y equals mx plus b form once again. They give us a little bit different details though. They do not give us 2 points. They give us 1 point that it passes through. That's going to be the only point we can use. Now, how do we find the slope if we're not given 2 points? Well, they have to give us some kind of a description or mention something about the slope in some way. They use this word perpendicular. We know perpendicular basically means it forms like a 90-degree angle. And that means these two lines have a slope that is opposite reciprocal. So they give us this random line that seems to be not related at all. We only need that line for its slope, and we really only need that line because we're going to take the perpendicular slope. So let's find out what is the slope. If you move this a little bit and then divide by 4, you can easily figure out what the slope of this line that we really don't need is. We don't really need this whole line. We just need its slope. That way we can take the opposite reciprocal. So the slope that we truly want is just 4. See how that works? So they give us a line, not to distract you. It's not like completely meaningless, but they give you this line just so that we can figure out what its slope is, because the line that we need to write about is perpendicular to that line. So kind of a roundabout way to make you do this problem, rather than just giving you 2 points directly. That would be a little bit easier. Let's plug this into the format now that we have the slope. 5 equals 4 times, what's the x value? 2. So here's 5 equals 8 plus b. We found a b value of -3, and now it's time to write the full equation of the line, 4x minus 3. Okay, that's 25, pretty much knocked out. So, I mean, about a quarter of the way, something like that. Plenty of pages. There's no shortage of pages. We're going to continue with talking about lines still in slope-intercept form. There are different ways that they can give you information about the line that they're interested in. So this time they just told us the slope. Slope is 3. That's really easy. You don't have to do any work to find the slope. Just read the word, slope is 3. And it tells us a point. They have to give us a point as well. The point they gave us is that it's the same y-intercept as this line. So we really don't need this line for anything in particular except its y-intercept. How do you find its y-intercept? Of course, anytime you want to find a y-intercept, you just make x equal to 0. And so that gives us some information about the point. Then when you plug in x equals 0, you get some more information about the point. you can learn that y equals 2. And there we go. You don't have to figure out what the b value is in this case because the b value is simply the y-intercept. That's why you might notice the name is called slope-intercept form. So in this case, we have the y-intercept already. We don't have to do any more work. We don't have to plug in the point. We can just plug in the y-intercept directly, and it's 3x plus 2. Okay, let's see. The last equation of the line in slope-intercept form that we have here, definitely a little more complex this time, but don't worry about it too much. Just realize that it says it's parallel to this line. What does parallel mean? Parallel means it has the same direction, which means this line has the same slope. And so if we can just simply rewrite this in a slightly better format, we can figure out what is that slope. So we have 3y, move everything else over, negative 2x plus 7. The plus 7 doesn't matter at all, but you do have to be careful with the x term because we're going to get the slope from that. So the fact that it goes to the other side means it's a negative. And then we divide by 3. So negative 2 over 3, x plus 7 over 3. But again, the over 3, 7 over 3 doesn't matter. All we need this for is its slope. Parallel means same slope. Okay, so there's the slope. There's the m value. But what about the point? How are we going to get this in slope-intercept form? Well, it gives us a point that says it has the same x-intercept. That's not quite the y-intercept that we need, but that's okay. It's still a point. And we can still use this point in the equation. How do we find the x-intercept? Of course, we have to set y equal to 0. Easiest thing in the world. So if we set that equal to 0, we just get x squared times, 0. It's pretty easy. Minus x to the 2/3 power plus 4 is 0. Of course, this 0 makes that go away very easily. And we have 4 equals x to the 2/3 power. Best way to solve this, we can take a square root of both sides. We can also cube both sides. And let's just do either one of those things. You need to do them both. You can do it in whatever order you want. I kind of recommend taking the square root of a number first. Make the number smaller before you make it bigger. And so we square root both sides. We end up with 2 equals x to the 1/3. Now, technically, we have a plus or minus 2 here. So do need to be a little bit aware of that. We'll kind of have to determine which one is the true x-intercept. It's possible. And then when we cube both sides, we're going to get plus or minus 8. So we kind of got to check, is it 8/0 or is it negative 8/0? Massive difference. Let's see. Let's go ahead and plug in. Let's plug in 8 to see how this works. So if we have 8 comma 0, that's 8 squared times 0 minus 8 to the 2/3 power plus 4. Okay, that's going to give us negative cube root of 64 plus 4. So negative 4 plus 4 seems to work. 8/0 seems legit. Let's see if there's a problem with negative 8. It's possible there's a problem with negative 8. So negative 8 squared times 0. Again, that part's just 0. Not really a big mystery. And then negative 8 to the 2/3 plus 4 equals 0. So this is going to be negative square root of negative 64. Oh, sorry. No, that's still a positive 64. Yeah, so I guess it doesn't really matter if we use a positive or a negative there. In the cube root plus 4. And again, that just gives us negative 4 plus 4, which is 0. So these are totally fine. Let's use the point 8 comma 0. Let's use that point. So we have 0 equals negative 2/3 times 8 plus b. So 0 equals negative 16/3 plus b. And so b equals 16/3. Like that. Okay, perfect. So our slope is negative 2/3. Our b value is 16/3. And that is our equation of the line, which is parallel to the given line, has the same slope as the line that they gave us, but it has the same x-intercept as this graph. Very weird graph. If you want to look at what that is on Desmos, I definitely encourage you to plug that equation in. Desmos is honestly a really great tool that you can use to try and figure out, what these graphs look like, especially if they're not your typical format. If it's not just like a simple quadratic, or if it's not just a simple line, for example. So here we have x to the 2/3 plus 4. Let's see what that looks like. And yeah, sure enough, we see two x-intercepts. I know you can't see that, but I'm looking at the graph on Desmos, and we see that there's an x-intercept at positive 8, and there's also an x-intercept at negative 8. So you know what I think we should probably do? I think we should probably draw up an equation of a line that's parallel, but is containing each one of those x-intercepts. It says same x-intercept. It might have been a typo. They probably wanted to put same x-intercept with like the parentheses s, because there's the possibility that it would be having more than one x-intercept. So yeah, I think it's probably a good idea to try to write through that one. Let's see, this would be something like, so this is for 8, 0. Now if we have negative 8, 0, really the only thing that's going to change here, you can observe that the only thing changing there is the symbol. Yeah, so the b value is just going to be opposite symbol as well. So it'd be something like y equals negative 2/3 x, but it'll be minus 16/3. And so this would be the equation for if we have negative 8, 0. Very similar lines. The only difference is and you notice the slope is the same. The slope needs to be the same. The only difference there is the y-intercept, because if it needs to pass through a certain point, if it passes through 8, 0 versus passing through negative 8, 0, that means the graph is going to be at a completely different place. Yeah. Okay, 28. Which of the points is farther from the point 1, 2? So farther, that means we're talking about distance, which means we're going to have to use the distance formula. So let's try to compare the distance between point 1 and 1, 2, and then also find the distance between point 2 and 1, 2, and see which is further. So this is just a little bit of simple Pythagorean theorem, right? The distance formula. The square root of x minus x squared, so 9 minus 1 squared, plus y minus y squared, so 3 minus 2 squared. That will simply be the square root of 8 squared, 64, plus 1 squared, 1, square root of 65. Now, distance 2 is going to use the same formula but with different points, so we're going to have 8 minus 1 squared. That's obviously smaller than 9 minus 1 squared. And then we're going to have plus negative 1 minus 2 squared. So this is going to give us 7 squared, or 49, plus negative 3 squared, or 9, which gives us the square root of 58. And that means that since this distance is larger, right, square root of 65 is bigger than square root of 58, obviously, then D1 is further. So point 9, 3 is further from the point. Okay. Here's a little more about slopes of lines. It's telling us the slope of the line through these 2 points, let's call this point 1, let's call this point 2, is equal to 4. So let's just set up the equation of the slope. T is the y1 and 2 is the y2. So we have 2 minus t over x2 minus x1, t minus 5 equals to 4. And solving that really just comes down to multiplying both sides by t minus 5. And you can easily solve this. It's like a two-step linear equation here. Get all the t's on one side, so maybe we'll add t, and then get all the numbers on the other side. So we'll add 20, add 20. Okay, so 22 equals 5t. T equals 22 over 5, 4.4. If you really want to put a decimal, that's fine. Okay, and the last one that we'll do before we take a little break here is going to be finding the value of some constant so that the graph of the equation passes through the point. What does it mean to pass through the point? That means that if you plug this x and y in, the equation is a true equation. So let's plug the y in, 13 equals 2k times, plug the x in, 7 minus 3 squared. All of that minus 5. This is very easy arithmetic, everybody. This is super easy arithmetic. Just plug your numbers in carefully. And notice that it's 2k times 4 squared. So it's 4 squared, 16, times 2k. We're not going to subtract the 5 from the 16. That is probably the most common mistake that a student would make on this problem. Add the 5 over. We have 18 equals 32k. And you can divide both by 2. 9 equals 16k, and that means k equals 9 over 16. Or for some of you construction nerds out there, that is approximately 0.5625.